All right, continuing our notes, we are going to now look at how to find molar solubility. We represent molar solubility with just the letter S. Okay, I know this looks like solid, but it's just supposed to be just the symbol for molar solubility. So, molar solubility is the concentration or molarity of the dissolved ions at equilibrium. Okay, it is different from the molarity of the solution because it is specific to only the ions that dissolve, not the ions added to the solution. So let me give you an example. If I add, say I had water and I added a salt, okay, into the water. So some ionic compound. Say I add 5 grams of it. And this salt is not completely soluble, okay? So I add 5 grams. If I wanted to find its molarity, I'd find how many moles per liter I had. So I convert this to moles and divide by my volume. Let's say I have 1 liter, okay? But that would be its regular molarity. We've calculated those many times, okay? Molar solubility would be how much of this 5 grams actually dissolves and breaks apart into ions. So let's say we add 5 grams, but only 1.5 grams of it actually dissolve into its little ions, okay, break apart into the little ions. Then the molar solubility would be this in moles divided by our volume, okay. Now, we are going to figure out how much actually dissolves because it's based on our KSP value, okay. That solubility product helps us figure out how much is actually dissolving. The equilibrium is there that we create. So to find our molar solubility, it's not actually too bad to do, okay? So it says we want to find that molar solubility of MgF2, and it gives us our KSP. It says at 25 degrees Celsius, it's this value. So remember, we can dissolve more of a salt when we change temperature, so that's why they specify the temperature on a lot of things. So just saying, at this temperature, all of this calculation will be true. If we change the temperature, it won't be true anymore. So, a couple of things we can always do. Remember, we can always see how this breaks apart from its solid into its ions. So we've got magnesium ion, that's in the second group, so it's 2+. And then I've got 2 fluorines, so 2F minus aqueous. Okay. So we can always write that. We can also always write the KSP expression based on that, which would be magnesium 2+, and F minus squared, right, because it has a coefficient of 2. All right, so what we want to do is figure out this molar solubility, okay? The way we look at this is that if we had, we kind of treat this like a little rice table, okay? Now these rice tables are very basic and they kind of end up being the same thing every time. Well, not every time, but if you've got like a 1-to-2 ratio, you're going to see the same pattern form. If you had a 1-to-1 ratio, you would see the same pattern, that kind of thing. So when we have a rice table and it has a solid, we get to cross that part out. We don't care about it. So let's assume that we start with our chemicals separate, right? We got our solid and then we've got our liquid. So none of it has dissolved to start. And then when we dissolve it, we are adding to this side, right? Because it's dissolving. So instead of using X, we're going to use S because that's going to help us figure out that solubility, okay? So we add S, and here I'm going to add 2S because I've got a coefficient of 2, right? This is going to produce twice as many ions when it breaks apart. So we get S and we get 2S, all right? Now, we are going to figure out what that, we need to solve for S, essentially, okay, that solubility. Now, we do have a KSP expression. Again, that's something we can always write, and we have a KSP value. So I'm going to replace my KSP with that value, and I'm going to replace my magnesium and my fluoride with my values here. Okay. Now here is where I see 99% of the mistakes on these, is not paying attention to how this is squaring and the calculation here. So I have S. I'm going to leave that by itself for now. I have 2 squared and I have S squared. So 2 squared is 4. S squared is S squared. Now I'm going to then multiply it by s again. So now I have 4s cubed. All right. So this is going to be the same thing anytime I have a 1 to 2 ratio on my ions, because one of them is going to be s, one's going to be 2s, and we're always going to get the same thing, which is kind of convenient. Okay, so there's our equation here. This I just brought down, right? It's always equal to that. Now we want to isolate our s. So first we have to divide both sides by 4. Okay, so I'm just going to move this over here. So I've got 16 times 10 to the negative 11. I can't type. Divided by 4. So 1.29 times 10 to the negative 11 equals, I've canceled that, so s cubed. So now we need to cube root this. Now if you've never done that in your calculator, sometimes people don't know how, and that's okay. So I'm going to leave my answer in there. Here's what we want to do. If we were square rooting something, then that's the same as raising it to the 1/2 power. Okay? If I was cube rooting something, that is the same as raising it to the 1/3 power, which I find easier to plug into my calculator. So I've already got my answer. I'm going to raise that. I'm going to put in parentheses 1/3, 1 divided by 3. So we're raising it to the 1/3 power to cube root it. And there's our answer. So 2.34, let's see, we had one decimal place or two. We had 2. So 2.35 times 10 to the negative 4 is your mole is S. So that is your molar solubility. So you could put molarity after that, and that is your molar solubility. Okay? So molar solubility is essentially solving for S here. Okay? And what it tells us is that this is the concentration of those ions. No matter how much solid we dump in there at 25 degrees Celsius, this is going to be how much actually dissolves. Okay, that's your molarity of your solution that actually dissolved, not how much you added, but what broke apart. Okay. Now it says, what are the concentrations of Mg2 plus and F minus in the saturated solution? So our concentrations at equilibrium are right here, S and 2S. So the concentration of magnesium is the same as our S value, 2.35 times 10 to the negative 4th molar. And my concentration of F is 2 times that. So 2 times 2.35 times 10 to the negative 4th. I get 4.7 times 10 to the negative 4th. And I'm going to keep those sig figs, so 4.70 times 10 to the negative 4th. So I'm just plugging back into here, figuring out, okay, I know at equilibrium they're S and 2S, and I'm just multiplying that out. Okay. Okay, let's look at another one. So calculate the molar solubility of aluminum hydroxide. It gives us our KSP. So we're going to try another one. So a couple things we can always do. We can always write the reaction of how this breaks apart. So we get aluminum, which has a 3+ charge, and we get 3 hydroxides that are negative. Okay, so this is a 1 to 3 ratio. So we're going to get, when it's equilibrium, got my double arrow, there we go. So we're not going to get S and 2S, we're going to get something like S and 3S. A bit different here. Okay, we can also write our KSP equation. So Al3 plus and OH cubed. Okay, remember we leave out our solid, so we don't have a denominator. So now again, I'm going to write the little rice table. We don't have any solid. We're starting with none of this dissolved. We're going to add to this side, and we don't know what the amount is, but it's S and then 3S because of our coefficients. So S and 3S. Now, if you're starting to see the pattern of what happens here, right, we get S and 2S, S and 3S. You don't have to show this rice table every time, but I often see people forget that coefficient, and that's where we get issues. All right, I'm going to replace my KSP with the number 1.9 times 10 to the negative 33. That is not very soluble at all, right? Negative 33, that favors the reactants a lot. For aluminum, I've got S. For hydroxide, we've got 3S cubed. So we got to simplify this and be really careful on that part. It's 10 to the negative 33. All right, so I've got S. 3 cubed is 27. S cubed. All right, so then I've got 1.9 times 10 to the negative 33 equals S times that, so 27S to the 4th power. Ugly. All right, I'm going to divide by 27 on both sides. Move over here. So I've got 1.9 times 10 to the negative 33 divided by 27. 7.0 times 10 to the negative 35 equals S to the 4th power. So let's think about this. If square rooting is raising to the 1/2 power, cube rooting is raising to the 1/3 power, then 4th rooting it, we're going to raise it to the 1/4 power. So again, I've got my number in there. I'm going to raise it to the 1/4 power. And there's our value. So S equals 2.9 times 10 to the negative 9. And that's my molar solubility. So that's basically my molarity. How much molarity of my solution if it is saturated, actually dissolved. Now this one kind of continues on the next page. So we'll just keep this part up best I can here. So this is similar to the other part B, where the concentrations of each ion in solution at equilibrium. So aluminum is the S, so 2.9 times 10 to the negative 9th. And our concentration of hydroxide is 3S, which is 3 times that value, which equals 3 times 2.9 times 10 to the negative 9th, 8.7 times 10 to the negative 9. Okay, and there's our answers to that one. All right, last question. Kind of giving us a different angle of looking at this. So if the molar solubility of this is 2.9 times 10 to the negative 17, so that is our molar solubility, that's S, what is the KSP? Let's do the same thing we did with the other ones. We're going to write our equation, our reaction, KSP equation, all that stuff, so we can see what's going on. All right, now silver is a transition metal, so I'm not writing its charge yet. Sulfur always has a charge of 2 minus, so silver, I have 2 of them, so they each would have to be positive to give us 2 plus, 2 minus. Okay, there's my reaction. I know we want to find the KSP of it, and its equation would look like silver squared times sulfur. Now, we know our molar solubility. We know what S is. So let's just look at this. If we had our little rice table, if we started with 0, we'd add 2S here because of the coefficient and add S there. And this is just the solubility, not sulfur. Okay, so don't mix those up. So we get 2S and S. So if this is S, that's our molar solubility, then silver would be 2 times that. So 2 times 2.9 times 10 to the negative 17th. And this would be 2.9 times 10 to the negative 17th. Oops. Running out of space there. Okay, so 2 times 2.9 times 10 to the negative 17th gives me 5.8 times 10 to the negative 17th. So these are the two values that we want to plug in to find our KSP. 5.8 times 10 to the negative 17th. We're going to square that. Sulfur, we've got 2.9 times 10 to the negative 17th. So KSP equals, let's see, I've already got my 5.8, that value in there, so I'm going to go ahead and square that. Multiply by 2.9 times 10 to the negative 17th. All right. 9.8 times 10 to the negative 50. That's quite the KSP value. So when we get something like negative 50, that is favoring the reactants a whole lot. This barely dissolves. When we're talking about solubility rules and something being soluble and insoluble, we would consider this chemical basically insoluble. We can see it because this is such a small value. So our equilibrium mostly lies towards this. Okay. So our first part of this is some practice on writing, splitting things up, writing what they would look like if you separate them into their ions, and then writing their KSP expressions. You've got some stuff about concentration. If it gives you the concentration of your saturated solution, then you can find the concentration of each ion. We just do a mole ratio for those, I believe. Did we do one like that? Yes, oh we did, okay. We can write the reaction, write our equilibrium expression, calculate KSP, all of that, okay? And then it goes from there with calculating your molar solubility and everything, okay? Let me know if you've got questions. You guys got this.